In the previous section, we used pipelining to increase the throughput or speed of a single cycle time loop. By the end of this module, you will be able to define fixed point data type terminology. Okay, so now we're in lesson 7, signal processing. So first we'll talk about using fixed point data types. We'll talk about using single precision floating point. We'll also talk about performing FPGA math and analysis, also how to perform high throughput math, how you can integrate third-party IP into your FPGA VI, and we'll talk about additional resources as well. So in this lesson, we'll be talking about how to do some signal processing on your FPGA VI. So after you acquire a signal, or before generating a signal, you might need to process it on the FPGA. So you might need to do some calculations, you might need to do some arithmetic, run it through algorithms, filters, or FFTs, and things like that. So this is all part of signal processing. So the signal processing that we're going to talk about right now is, as we see on this graphic, is going to be the signal processing that's happening on that FPGA VI. So now we're going to talk about using fixed point data types. What's so good about fixed point data types? Well, they provide some of the flexibility of floating point data type, but they also maintain the size and speed advantages of integer arithmetic. So what that means is it's going to allow us some flexibility to get something close to floating point calculations, but because of the size and speed advantages, it's going to take up a lot less space on your FPGA. So when you're using a fixed point data, you're going to need to configure the appropriate range when you're doing math and using the data types, and we'll talk about this more in later slides. Also, one thing to be aware of is the fixed point data type is going to be limited to a maximum size of 64 bits. Okay, let's talk about fixed point data types. So a fixed point is a collection of data types with different ranges of values. So these ranges are going to be defined by a minimum value, a maximum value, and a delta. Okay, and the way that those ranges are going to be determined are based on 3 different factors that we're going to talk about in the next slide. So one is sign encoding, another one is word length, and lastly there's integer word length. So these 3 values are going to determine what the range of that fixed point data type is going to be. So let's walk through these. So what is sign encoding? This is the option that determines whether the fixed point data is going to be signed or unsigned. So if it's signed, it can represent positive and negative numbers. If it's unsigned, it'll only represent positive numbers. Another one is word length. So this is going to be the total number of bits that are used for your fixed point data. So this is going to kind of determine the precision that you have with your fixed point data. And lastly, there's integer word length. This is going to be the number of bits used in the integer portion of your fixed point data. Okay, so this will make a little bit more sense on our next slide when we go into a demo. So for this demo, we're going to observe how sign encoding, word length, and integer word length affect the minimum, maximum, and delta of a fixed point data type. So if you want to follow along, you can go to your exercises folder and open up the demonstrations folder and go to the fixed point data type folder. So let's go into LabVIEW now. Okay, so let's go into LabVIEW and open up this demonstration. And let's go ahead and run this. Okay, so in this demonstration, I'm going to go through some of this VI and show you how to use it to try to understand fixed point data. If you want to understand it a little bit more, you can try to open it up yourself and play with it more after this demo. Okay, so let's talk about what fixed point data is. And what I'm going to try to get you to understand in this demonstration is how sign encoding, word length, and integer word length affect your fixed point data. Okay, so in this demonstration, we're going to use a sign encoding of unsigned, which is represented here by this plus sign. The word length here is going to be 8, so that means we're using 8 bits of precision to represent our data. Okay, so that's why we have 8 digits here. And then lastly, what we're going to play around with is what the integer word length is going to do for this configuration. Okay, so right now, again, we have 8 digits of precision here, and let's take a look at the integer word length. So what that's saying is there's going to be 8 digits here that are going to represent our integer length. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, all representing integer data. Okay, so we've got 2 to the 0 here, 2 to the 1, 2 to the 2, and if you add this all up, it's going to be 255 is our maximum in this current configuration. If we want to look at our minimum, if we set these all to 0, notice our minimum is 0, and if we look at this this bit, we're going to get a delta of 1. Okay, so not too bad so far. Now let's see what happens if we shift this over the decimal point to here. Now notice that we have 4 digits here that are representing our decimal, and 4 digits here that are representing our integer. So notice over here, the integer word length now is 4. Okay, so if we take a look at this, what's the maximum that this can represent? So if we do 1, 1, 1, 1, we have 15 here, and then 1, 1, 1. This is going to represent the decimal portion, or the fractional portion. So if we take a look at this, our maximum that we can represent with this configuration is 15.9375. Okay, and the minimum delta that this can represent is 0.0625. Okay, so real quick, I'm just going to show you another thing here, and I can actually bring this out to here. Okay, so if you have an integer word length of 9, this is the configuration that you're going to get. So again, your minimum is going to be 0, but your delta now is going to be 2. And your maximum that you can represent with this configuration is 510. Okay, so let me close that down to zeros again, and let me show you the other direction. So if we go in the other direction, notice that your integer word length can actually be -1, and this is how that would be represented with the bits. So the minimum again is 0. Here, the minimum delta that you can achieve is this number right here, and the maximum that you can achieve with this particular configuration is 0.4980, and so on and so forth. Okay, so now you can see how the integer word length here can be negative, and it can also be something that is greater than your word length. So hopefully you've gotten a better understanding of how sign encoding, word length, and integer word length affect what your range of your fixed point configuration is going to be. Now you can define fixed point data type terminology. Next, we will configure fixed point data types and describe the effect of arithmetic on the fixed point data type. In the previous section, we defined fixed point data type terminology. By the end of this module, you will be able to configure fixed point data types and describe the effect of arithmetic on the fixed point data type. Okay, so in this slide, we see a picture of the context help. So if you were to take your mouse and turn on the context help and hover over any fixed point data, so for example, if you're hovering over a fixed point control or indicator or a wire that contains fixed point data, you'll see the context help populate with information about that fixed point configuration. So for example, you'll see the sign encoding there, you'll see the word length, you'll see the integer word length as well. And remember, based on those three, that's how the minimum, maximum, and delta for that fixed point data is calculated. There's another thing over here called overflow status. We'll talk about that a little bit later in this lesson. So in this slide, we see a couple of examples of fixed point representation and how that affects the delta, minimum value, and maximum value. So if we take a look at that first one, we see a U8. So if you're trying to represent a U8 data type, you would have a delta of 1, a minimum value of 0, and a maximum value of 255. So that would correspond to a fixed point configuration that is going to be unsigned. It's going to have a word length of 8 and also a integer word length of 8. And as we look at these different examples down here, you'll see how the different representations will affect those delta, minimum, and maximum values. So in the previous module, we were able to talk about and show a demonstration of fixed point and how changing those numbers was affecting our delta, minimum, and maximum values. So here we just have a table that kind of shows it again and shows you a couple of different configurations. So in this slide, we show how you would actually configure that fixed point data inside LabVIEW. So in LabVIEW, first you would have to have a numeric control that is of a fixed point data type. So to do that, first you would put down a control, and then you can right-click it and change the representation to fixed point. And then after that, you can right-click that control and go to Properties. This will launch a window, and if you go to the Data Type tab, notice that you can change the representation there too to fixed point if you haven't already. And then in the configuration, the things that you would change would be the encoding. So first of all, you have to figure out, okay, is my fixed point data going to be signed or unsigned. So choose one of those. And then after that, you can take a look at the word length and the integer word length. So you can adjust these, and as you're adjusting both of the integer word length and the word length and the encoding, you can look on the right side and you can see the range change as you're doing that. So you can keep adjusting those values until you get the right minimum, maximum, and desired delta for your fixed point data. So on this slide, we have a question about fixed point arithmetic. So if we take a look at this block diagram real quick, what is the fixed point configuration of the output? So let's think about this for a second. So if we have two fixed point inputs going inside the addition, we see that they're unsigned, and we have a word length of 10 and an integer word length of 6. Okay, so if we were to keep that same configuration for the output, would that be able to accommodate the maximum value? For example, if you took a look at the inputs and you just had the maximum value that's allowed by that configuration, what would the output configuration need to be to accommodate that? Would it need to grow? So we'll talk about this in the next couple of slides. So let's talk a little bit more about fixed point arithmetic. The range of the output values of some fixed point arithmetic function will be large enough to accommodate the largest possible input values up to 64 bits. So what this is saying is when you take an arithmetic function, it's going to take a look at those inputs, and then it's going to automatically output a fixed point data type that can accommodate the largest possible values that those inputs would have created in that arithmetic function. Okay, so the point of this is it needs to be large enough so you don't lose any data from the operation, because sometimes you're going to need to grow that fixed point configuration to accommodate a higher maximum, for example, or a more precise delta. And then the 64-bit, that limitation is just a limitation of the fixed point data type itself. So the fixed point data type, the highest precision that it can represent is 64 bits. So the maximum word length is going to be 64 bits. So let's look at the second bullet. So LabVIEW is going to propagate the range of those values along each wire. The representation is then calculated to be as small as possible without losing data. As you're using these fixed point arithmetic functions, it's going to propagate these ranges throughout the wire. As you're going through different arithmetic functions, each function is going to keep adjusting the output to make sure that you're not losing any data. Okay, so in some cases, it's going to have to grow that fixed point configuration to be larger so it can accommodate the largest possible values that could come out of it. But at the same time, LabVIEW is going to keep that growth to a minimum. So it's going to be large enough not to lose any data by default, and it's going to use the smallest configuration that is able to accomplish that. So let's take a look at a couple of examples. So in the next couple slides, we'll talk about how that works with addition, subtraction, multiplication, and division, and you'll see more specific examples with that. So let's take the example of addition. So remember, the range of the output should be large enough to accommodate the largest possible input values. So in the addition example, let's take a look at the configuration of the two fixed point controls. So if you were to set those controls to their maximum values and add them together, the output wires configuration would have to be larger to accommodate that maximum possible sum and also not to lose any accuracy or data. So for addition, the integer word length must be 1 bit longer, resulting in the word length also increasing by 1 as well. The arithmetic functions automatically adjust the fixed point configuration of their outputs to accommodate their inputs without losing any accuracy. So as you can see, on the left we have that original unsigned 10 and 6, and then on the right side, notice that the fixed point configuration had to grow. So it's still unsigned, but it's going to grow to 11 and 7. Okay. So if we take a look at the subtraction example, it's going to be similar. We're going to have to increase the word length and the integer word length as well. But if we take a look at the signed encoding, we see that that's changed as well. So in subtraction, whether or not the inputs are signed or unsigned, the output must be signed, because subtraction you could possibly get a negative number. So here we see arithmetic examples of multiplication and division. So one thing I just wanted to point out here is that multiplication and division are going to grow even more. So in the previous slide we saw with addition and subtraction, it was growing the word length by 1. But over here, notice that the formula up there is showing you that the output is going to grow by A plus C. So if we take a look at that block diagram now for multiplication, notice that we have unsigned 10 and 6 for both of the inputs, and notice that the output actually grew a whole lot. So notice that it grew all the way to 20 and 12. So the output configuration is now using 20 bits of precision. Okay, so if you think about this, if you keep multiplying things, so if you have a string of multiplication functions, your data is going to grow large very quickly. Okay, so just keep that in mind. And then we see the same thing with division. And the only thing I want to point out with the division is that there's a different formula for signed and unsigned. So you can see that up there, and again, you see that the output configuration grew by a lot. So notice that it goes from 10 bits of precision to 21 or 20. So just be careful when you're using these functions. They might quickly grow to the maximum 64 bits that you can represent with fixed point. Okay, so now let's dive into LabVIEW and take a look at a demonstration of fixed point math. Okay, so for this demo, I'm just opening up the solution file for exercise 3.1, and so we could take a look at this math VI. So let's go ahead and take a look at the block diagram real quick. So here, all we're doing is we have some I16s, and these are just normal integers, right? And we're adding, subtracting, and multiplying. Okay. So let's see what happens if we take the maximum value here. So I'm just gonna put a really high number, and notice that the maximum that an I16 can represent is 32767. So I can go lower, but I can't go any higher. Okay. So what happens if we take the maximum and add it by something like 10? Okay. So we know the correct answer, if you add it, should be 32777. So if we were to run this, notice that the addition, we do not get the right answer. So if we're using an I16 integer, it actually starts rolling over, right? So we get the incorrect answer here. And then subtraction, it just happens to be correct. And then the multiplication is definitely not correct either. The I16 wasn't able to grow to accommodate that new maximum. So let's contrast this with fixed point. Okay, so the first thing I'm going to do is I'm going to take these indicators and I'm going to go through their properties. Right now these indicators are I16s, but I'm going to make them adapt to the source. So what that does is whatever the data type of the wire coming in, the indicator is going to adapt to that. So I'm going to click OK. Because the incoming wire here is I16, these are not going to change. However, I'm going to change these controls and change their data type. And I'm going to change these from I16 to fixed point. So notice with the fixed point representation that it changed it to is going to try to do the equivalent of what we had before, which was I16. So notice that it's signed, just like an I16. And then the word length and integer word length are both 16. So if you take a look at the range here in the delta, this basically represents the same thing that's equivalent to an I16. Okay, except now it's a fixed point data type. So now I'm going to click OK. And let's try running it, and let's just see what happens. Okay, so I'm going to run this again with the same values, and let's see if we get the correct answers this time. So notice when we added these together, now we do get the correct answer, right? And the data type was able to grow to accommodate a new maximum. The subtractant is correct, and also the multiplication, which, you know, when you multiply these two, it gets much bigger than our original data type, right? But it was still able to get the right answer here. Okay, so now let's look at the block diagram again. And what I'm going to do is I'm going to open up the context help, and let's take a look at the data type here. So if we look at the controls, notice that it is our sign 16 and 16, and sign 16 and 16, okay, just like we saw in our configuration box earlier. Now let's go ahead and go over to the wire coming out of add. Notice that the output of the add was able to make the data type grow. So notice that it is now 1717, right, to accommodate a new maximum for addition. And then for subtraction, it was able to grow from 1616 to 1717. Okay? And for the multiply, notice that with the multiply, if we have the two maximum values coming in there, the multiply data type is going to have to grow a lot to be able to accommodate a new maximum, right? That new maximum is going to be very large. So it goes from 16 to 16, and if we look at the context help, it goes to 32, 32. Okay? So here we can see that the advantage of some of these fixed point functions is that they're going to grow to accommodate the new maximums and new precision that you need based on your calculation. Okay, so one thing I want to demo again, or not again, but one more thing I need to demo just to make things a little bit more clear again is, let's say I have a control, and let's say I need to figure out what the fixed point configuration needs to be. So I'm going to go into the properties and show you how you can do that. So first of all, I want to make this into a fixed point data type, so I'm just going to choose fixed point. And let's say this fixed point number, I need it to represent a plus or minus 5 voltage. Okay, so my maximum is 5 and my minimum is -5. So based on that, I know that it needs to be signed, right? Because I need to have positive and negative values. And let's see, so our minimum and maximum, that's pretty big, right? I just need to get something between 5 and -5. So let me go to my integer word length and decrease that until we get something a little bit more appropriate. So it looks like we're getting close. Okay, so -4 to about 4, that's not going to be big enough, right? Because I need to go all the way to 5 and -5. So let me increase this by 1. So now we've got our minimum and maximum that can accommodate a plus or minus 5 voltage. And here I can adjust the word length and get the appropriate delta, right? So the delta is going to determine how precise or how the resolution of this data type. So let's say I know that it needs to get a delta all the way up to something like that. Okay, so this is just a quick demo of showing you how you can configure your fixed point data type using the encoding, word length, and integer length based on your requirements of what your minimum, maximum, and delta need to be. Now you can configure fixed point data types and describe the effect of arithmetic on the fixed point data type. Next, we will configure the data type, rounding mode, and overflow mode of fixed point functions. In the previous section, we configured fixed point data types and described the effect of arithmetic on the fixed point data type. By the end of this module, you will be able to configure the data type, rounding mode, and overflow mode of fixed point functions. In this slide, we're going to take a look at how you would configure fixed point functions. If you right-click the multiply function, for example, and you go to Properties, and you look at the Output Configuration tab, so notice for this function we are using fixed point data type. By default, these functions will have the Adapt to Source checkbox up there enabled. Okay, so by default it'll be enabled because the multiply function, for example, is going to automatically grow the output configuration based on what the minimum is so it doesn't lose any data, like we talked about in the previous module. However, if you want, you can actually disable this and specifically and manually specify what you want that output configuration to be. So why would you do this? So if a compile fails due to lack of FPGA resources, then you can try to modify your fixed point code to use less FPGA resources. So by using this window, you can actually try to decrease the amount of precision that you're using if you know some additional information about your inputs that are coming in. For example, if you know the expected minimum and maximum input values for a function will be smaller than the minimum or maximum range of the input wire's fixed point configuration, you could potentially disable the Adapt to Source item and decrease the word length and integer word length of the output data type to values that reflect your expected range and desired delta of the function's output. For example, let's say we have analog input channel 0 input wire for the multiply function, and your application will always send a value to that analog input between -1 and +1, and you happen to know that already. However, the analog input 0 input wire, the wire itself, has a range from -8 to 8. So in that case, because you know it's only going to be between -1 and +1, we can go to the multiply function and kind of adjust the output configuration to use less bits, because we know we don't need to go and represent a minimum and maximum of plus and minus 8, and we can reduce that down to plus or minus 1. So if you are going to disable the Adapt to Source and you're going to manually specify what the fixed point configuration of the output is going to be, at that point, then you'll have to think about what rounding and overflow is going to do. So, for example, you'll have to figure out if a comes down to a case where you need to round, how you're going to handle the rounding. Or if your data gets too high or too small, what are you going to do when it overflows? And we'll talk about those in the next 2 slides. So let's talk about rounding. So rounding occurs when the precision of the input value or the result of an operation is greater than the precision of the output type. Okay, so if your output type doesn't have enough precision, it's going to have to figure out what you're going to do about that. So at this point, you'll have to select the rounding mode. Do you want it to truncate? Do you want it to round half up? Or do you want it to round half even? So first, let's talk about what truncate does. If you use the truncate mode, then it's going to remove the fractional bits, and therefore it doesn't require any additional hardware resources. However, this mode produces the largest mean error for most data streams. So in this case, it's just going to drop off the fractional bits that it can't represent. Now let's talk about the round half up. So the round half up option, it rounds the value to the nearest value that the output type can represent. However, if the value lies directly in between those 2 values, for example, let's say the 2 values are 1 and 2, and we have a value of 1.5. In this case, LabVIEW is just going to round to the higher of the 2. So if it's between 1 and 2, and the value is actually 1.5, it's going to round it to 2. Let's talk about the round half even. So with a round half even, it's going to round the value to the nearest value that the output type can represent again. However, if the value lies exactly in between 2 such values, then LabVIEW is going to check the value of the bit that becomes the least significant bit after rounding. If the bit is 0, then LabVIEW is going to round to the lower of the 2 values. If the bit happens to be 1, then it'll round it to the higher value. So essentially what this does is if we had 2 values and the value that you got was right in between, approximately half the time it would round down and approximately half the time it would round up. So it's a little bit more accurate. So this mode has the highest impact on performance. It's going to take up more resources, but it is more accurate than the truncate method, and it eliminates the bias towards the higher value that can occur if you use the round half up mode instead. So this is the default option that we have for rounding, just so we can make it the most accurate. Okay, so now let's talk about overflow. So what would happen if you happen to overflow? So let's say you went outside the range of your values and it went past the maximum. So overflow occurs when the result of an operation is outside the range of values that the output type can represent. So let's say your output type could only have a maximum of 255. What happens if the output was going to be like 257, for example, and it's outside the range that the output type could represent? Well, the behavior is going to depend on what you do with overflow mode. So one thing you can do is wrap. The other mode you can do is saturate. So what wrap does is it's going to discard the significant bits of the output value until it falls within the specified range. So you almost get kind of a rollover behavior if you're going to use wrap. The other one is going to be saturate. Now this is the default option. What saturate will do is it'll coerce the output value to either the maximum or the minimum, depending on which value is exceeded. So this option is going to take up more resources than the map method, but is going to, in most cases, be the more desired behavior. So for example, if you had a maximum of 255 and it went beyond that, it would just saturate at 255. As a rule of thumb, rounding half even and saturation overflow modes typically render the most desirable results. Rounding usually gives an overall more accurate fixed point representation of the input number. Saturation prevents outputs from jumping between the top and bottom of the fixed point range when the input numbers are outside the bounds of your fixed point data type. The only drawback is that rounding half even and saturation modes require slightly more FPGA resources compared to the truncate and wrap modes. So as you're selecting overflow and rounding modes for your different arithmetic functions throughout your program, try to use the same format for all related functions. This way, it doesn't get as confusing and you know exactly what the overflow is going to be and what rounding mode it is. When you start mixing different modes together, then it's kind of hard to keep track of. Also, mixing fixed point configuration types can start to cause data loss as well. So if you're using these math functions and you're specifying the output configuration manually to save resources, make sure that you configure these math functions to handle saturation, truncation, and rounding as needed. Okay, so let's talk about the best practice for doing some fixed point algorithm development. So what you shouldn't do is just starting off in fixed point and making your algorithm there. Typically what you want to do instead is you want to start symbolic. So you can go to the symbolic representation, the math of what you want your algorithm to do. Okay, so once you figure out what that symbolic representation is, then try to implement that using floating point. So floating point is a lot easier to use than fixed point, right? You don't have to do all these different configurations. So first try to make your algorithm in floating point and make sure it works there. So make sure you test that floating point algorithm thoroughly and make sure that the fixed point algorithm looks right. Once you've confirmed that, you've got something nice to compare with. After you do that, then go ahead and create that same algorithm using your fixed point data type. Okay? And then you can compare the results of your fixed point algorithm to your floating point algorithm and verify what is your acceptable accuracy. So once you're done doing that, and remember you're going to be doing this on your FPGA VI and you want to simulate this on your development computer. And then once you get that algorithm looking nice and having the acceptable accuracy, only then should you compile and test it on the FPGA. Okay, so at this point, if you're able to, go ahead and do exercise 7.1. In this exercise, it brings it all together where you're using fixed point, and then it also shows you when you'd want to try to optimize that fixed point and do that output configuration of your arithmetic functions. So for now, I'm just going to go and walk through this, and if you want to get experience yourself, go ahead and do it yourself too. Okay, so what I've done here is I've opened up the solution file for exercise 7.1. So what I'm going to do is I'm going to open up the fixed point configuration part 1. And what we'll do in this demo is walk through what you would have done in the exercise. So let's go to the block diagram. Okay, so let's set up this scenario here. So what we have here is a 9234 module, and it's an analog input module, and the fixed point configuration that's coming out of that channel is going to be signed, and then 24 and 4. Okay, that corresponds to a minimum of -8, a maximum of about 8, and this delta over here. Okay, so in this scenario, we just happen to know that the analog input coming in is going to be between +2 and -2. Okay, even though this module can get values above that all the way to -8 and 8, we just happen to know in our case that the incoming values on our channel are going to be between -2 and 2. Okay, so that's what this function here is doing. It is coercing this data, so the simulated data that's coming in, since we're going to be simulating this, is going to be between 2 and -2. Okay, and then what we wanted to do with that data is we wanted to scale it. So in the first part of the exercise, you would have put down a multiply function, and then you want to multiply it by 5 to get our result. Okay, so this is kind of representing our algorithm here. So when you're putting down a fixed point constant, you want to make sure that here we're trying to represent a 5. So we want to use a fixed point configuration that's the smallest it can be that can still represent a 5. So let's take a look at the properties for this and look at the fixed point configuration. So for 5, let's go and look at the data type. So 5 is not negative, so we can go ahead and choose unsigned. And then based on our requirements for 5, if we have a fixed point configuration that can do 0 to 7 and a delta of 1, that's going to be the smallest that we can do that can represent the number 5. Okay, so that's why we have a word length of 3 and integer word length of 3. So let me click cancel here. So make sure you configure your constants accordingly, and then here we're going to multiply that and get our result. So let's go ahead and go to the front panel and see what happens. So notice we get -2 and -10, and then we get a value here, and that's also multiplying it by 5. So we verified that this is working correctly. Okay, so let's take a step back real quick and take a look at this from a high level. So let's say we try to compile it, and the compile was successful. Then we're pretty much done, right? Everything works, and we're good to go. However, let's say we developed some algorithm and we hit compile, and then that compile was failing. Well, maybe what we need to do is we need to go back to our fixed point algorithm and do a little bit more optimizing to help that compile succeed. So let's say that happened and we had to go back into our fixed point algorithm here and make it a little bit more optimized. Okay, so if we look back at our scenario, this wire here, this fixed point wire, has a configuration of ±8 and then 24 and 4, right? And this is going to give us a maximum of 8 and a minimum of -8. However, we happen to know that those values will actually only be between -2 and 2. Okay? So based on that, we can actually decrease the precision that's coming in here to figure that out. Okay? So if you think about it, and we run through the math in our heads, well, if we know that the values coming out of here are only going to be between -2 and 2, if we multiply that by 5, we know the output of this multiply function is only going to be between -10 and 10. Okay, so based on that, we can right-click and go to the properties of our multiply and adjust the output configuration accordingly, right? So notice when I right-clicked and went here, the output configuration by default for arithmetic functions is going to be adapt to source. However, in this case, we want to specify our fixed point representation to save some space. So I'm going to deselect that. And now notice that we can go to encoding and range and set this ourselves. Okay, so right now, the minimum is -56 and the maximum is about 56, right? And this was based on the configuration of the wire. However, we know some extra information, and we know that based on that extra information, the minimum is actually only going to be -10 and the maximum should be 10. So we know the delta should still remain the same, but let's go ahead and adjust the integer word length to get something that's a little bit better. Okay, so we need to go from -10 to 10, so this one's too small. Let's increase it by 1, and now we get our right minimum and maximum. Okay, and then now notice that we're going from 27 bits for our word length, and I can adjust this back down to get that same delta, and now we've saved some bits here in our fixed point algorithm. Okay, we've gone down from 27 to 25. So now I'm going to click OK. Oh, the other thing I wanted to show real quick, let me go back. The other thing I wanted to show real quick is now you can adjust the rounding mode and the overflow mode. In this case, we're going to do round half even, which is the default, which is a little bit more accurate, and then saturate as well, because if it goes over that, we just want it to stay at the maximum or stay at the minimum. The other thing I want to do is I want to include the overflow status. Okay, so what this is going to allow me to do is if it does overflow and it saturates, I want to know whether or not I'm getting some overflow values. Okay, so I'm going to click OK. Okay, so what I'm going to do now is I'm going to go to, well, before I go to that, notice that the multiply has a blue dot here. The blue dot indicates that I'm manually doing some coercing here. Okay, that I've specified what the output configuration is going to be. So let me go to my properties of result indicator, and I'm going to change this to adapt to source. Okay, so that way it's just going to adapt to whatever the incoming data on that wire is going to be. Okay, so now let me go back up here to the front panel. I'm going to right click on the result. I want to see whether it overflowed or not, so I'm just going to do overflow status LED. Okay, so now let me go ahead and run this. And notice that the simulated result is correct, and the simulated results will never be over 2 or -2, right? It's never going to be greater than 2 or past -2. So we get all the correct values and we're not getting any overflow. Okay. However, if we had some data coming in here and it was like -2.5, this result would saturate at -10, but this overflow LED would light up like that. Okay. Okay, so let's look at the discussion questions. When should you allow the functions to automatically grow the size of the fixed point configuration? So one thing you can do is when you're first writing your algorithm and you're using fixed point, you can just let the functions automatically grow, and then you can try that compile. And if the compile succeeds, then without doing any extra work, the compile already succeeded and you're good to go. However, if it fails, then maybe you might need to go back in there and do some optimization. So when should you manually configure the fixed point configuration of the function output? Like I just said, if the compilation failed, then you need to go back in there and try to optimize it to save some space and possibly get some speed benefits as well. Now you can configure the data type, rounding mode, and overflow mode of the fixed point functions. Next, we will use the single precision floating point data type in FPGA VIs. In the previous section, we configured the data type, rounding mode, and overflow mode of fixed point functions. By the end of this module, you will be able to use the single precision floating point data type in the FPGA VIs. In this section, we'll talk about using the single precision floating point data type in LabVIEW FPGA VIs. So starting in LabVIEW FPGA 2012, LabVIEW FPGA began supporting the use of single precision floating point data type in FPGA VIs. So as you can see here, there is a single precision floating point control there, and there's also a function that you can use to convert data into a single precision floating point. So one of the main benefits of using floating point in FPGA is that it's easier to rapidly prototype than fixed point data type. We saw before with fixed point data type, there's a lot of configuration that needs to happen. With floating point, a lot of algorithms are already developed in floating point, so it's a little easier to use floating point. Some of the caveats though, typically using floating point is going to require significantly higher FPGA resources than fixed point data type for some operations. Also, most functions cannot perform floating point operations inside a single cycle time loop. So if you're trying to do some floating point operations inside a single cycle time loop, then it's probably not going to compile. So in this slide, we see a couple of use cases for using floating point. So we'll talk about each of these use cases in the next coming slides. So let's talk about this use case. Let's say you're trying to free the host processor to perform other operations and use single precision floating point conversions with I/O. So if on your host, when you're sending the data there, the host is the CPU usage is pretty high, and you're trying to save some CPU usages on the host, what you can do is you can do some of that logic down on the FPGA. So in this block diagram, we see that we have we're getting some fixed point data from our I/O module. We're doing some sort of fixed point algorithm on it, and what we're doing is we're handling the conversion of that fixed point and changing it to a floating point number here on the FPGA, and then we're going to be sending it up to the host. So we'll talk about that last node on there in a later lesson. But this way, instead of handling that conversion on the host, we handle it on the FPGA instead, so we can conserve the resources on our host. So for example, you might receive a voltage value as a fixed point data type, and maybe you convert the voltage value into a useful engineering unit value. And then after that, you convert that fixed point data type to a single precision floating point type and send that to the host. That way, the host processor now doesn't need to use any CPU resources on that algorithm and that conversion. Okay, so let's talk about this use case. Let's say you want to operate on data from multiple inputs or outputs that return different fixed point data types. So if we look at this block diagram real quick, we've got an FPGA I/O node. Notice that the I/O node contains two different modules, so module 1 and 2, and those modules have slightly different fixed point configurations. There's a sign 16.5 and a sign 21-4. Well, if we wanted to do some common code on both those numbers, we couldn't because the data type is different. So one thing we could do is we could just convert both of those wires to single precision floating point, and then here we bundle it, or we build it into an array, and then we send it to a for loop. And because now both of those wires are the same data type, namely single precision floating point, we're able to handle that with common code. Another use case for using floating point is, let's say you need to represent very large and also very small numbers in the same data path, such as with accumulators. So over here, we have a block diagram of an accumulator. So notice that we have data coming in, and we have small data possibly coming in on that top wire. And then on that bottom input to that addition, it could be a very large number because you're just accumulating and you're adding a small number to a potentially large number. That's just accumulating the sum. Another use case that is like this is averaging. So when you're averaging, you're doing somewhat the same thing, right? You're adding small numbers to possibly a very large number and then averaging it. Okay, so on this slide, we see that you can also use floating point to rapidly prototype. So, for example, again, it's pretty easy to get floating point algorithms and test them. So what you can do is you can take your I/O. So notice we've got fixed point data type coming from our I/O node, and we're immediately converting it to single precision float. And then now we're able to go ahead and run that on a floating point algorithm. So you can try this, and it'll probably take up more space, but if it compiles correctly, then you're already good to go and you didn't have to go to fixed point. However, later on, you can try to convert it back to fixed point if you want to try to optimize some of your FPGA performance or resource usage. So in this slide, you can look at some additional resources to find out more information about using floating point in FPGA. So some best practices that we described here will also be in here. So if you go to your LabVIEW help, if you look up these 3 topics, you can get a little bit more information on the details of this. You can also see functions that support the single precision floating point data type, and there's a list of those in the help as well. Now you can use the single precision floating point data type in FPGA VIs. Next, we will describe 3 types of FPGA math and analysis VIs. In the previous section, we used the single precision floating point data type in FPGA VIs. By the end of this module, you will be able to describe 3 types of FPGA math and analysis VIs. In this section, we'll be describing performing FPGA math and analysis with some of the functions that are provided on this palette. So if we take a look on the right, we have a screenshot of that palette. And notice there's a lot of configurable and pre-built functions available for you. So there's stuff for mathematics, measurements, there's control things. For example, there's a PID VI in there. There's filtering, signal processing, and high throughput math, and there's a lot more as well. So feel free to browse through this palette and see what's available. So in the FPGA math and analysis palette, there's going to be 3 types of nodes that I just want to go over real quick. So one is a primitive, and we're going to talk about non-configurable express VIs and also configurable express VIs after this. So primitive, you can think of this as just a normal function. So notice that it's got a yellow background. So you're not going to be able to double click into it and look at a block diagram for it or anything. It's just a low level function. And the primitive that we see here is essentially a feedback node, or it can also be called a Z-transform delay node. Now let's talk about a non-configurable express VI. So if you take a look at the linear interpolation VI that's there on the left, it looks like a normal VI, but if you were to try to double click it, you wouldn't see a block diagram, and you also wouldn't see a configuration window. So if you see that behavior, that's a clue that it's a non-configurable express VI. So why is it an express VI behind the scenes? Well, the express functionality that it's bringing is, you notice that it's dealing with fixed point inputs and fixed point outputs, right? So what it's actually doing is it's taking those inputs, and behind the scenes, it's adjusting the fixed point configuration of the output to accommodate that, kind of like we saw with the arithmetic functions earlier. Okay, so if you wanted to take that VI and for some reason you wanted to customize it and add your own logic, you could. And the way that you would do that is you could right-click it and then select Convert to Sub-VI. And then it would look something like we see on that yellow node. And it now looks more like an express VI. At that point, you can double-click it and look at the logic, and you can try to adjust it. Just know that if you do this and you save your own custom VI, then you lose that express capability of being able to adjust for the function to automatically adjust the output data type based on the input data type. So for the most part, you probably won't be making your custom VI from this. You'll probably just use these non-configurable express VIs as is and know that the output data type is already going to be adjusted based on the input data types. And we also have the familiar configurable express VIs. So these are just going to be the VIs that you see on the palette that have that blue border or a purple border. So if you double click these, it's going to launch a GUI for you to graphically set settings and things like that. So these are more like the familiar express VIs that you've worked with before. Now you can describe 3 types of FPGA math and analysis VIs. Next, we will describe the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. Now you can describe the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. Next, we will use the 4-wire handshaking protocol when using multi-cycle FPGA math and analysis VIs. In the previous section, we described 3 types of FPGA math and analysis VIs. By the end of this module, you will be able to describe the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. Okay, so let's take a look at VI execution modes. Notice when I double-click this FPGA math and analysis express VI, I'm able to look at the execution mode. So the execution mode, you can choose either outside a single cycle time loop or inside a single cycle time loop. So let's talk about outside a single cycle time loop first. So if you're putting this function outside of a single cycle time loop, then it's just going to think of it as executing like any other function. So it's basically going to execute, and then it's going to take an input and give you the output. It might take a couple of clock cycles for it to do it, but it's just going to take an input and give you an output. Pretty simple. However, let's say you want to put that function inside of a loop, and you want to make that loop be able to run very quickly, and you want to increase the throughput of that so you can get outputs at a faster rate. In that case, you would need to put this function inside a single cycle time loop. So if that's the case, then you would set the execution mode to inside single cycle time loop. And notice that there's other things that might pop up. For example, notice that latency now shows. So there's a latency that's associated with it now of 6 cycles. Also, take a look at the way that the ExpressVI looks now. You see there's output valid, input valid, ready for output, ready for input. And those are handshaking terminals that come into play, and we'll talk about those a little bit more later as well. So if you're looking for a higher throughput for that function, then that's when you would put it inside a single cycle time loop, and this is the use case that we'll talk about in the next couple of slides. Okay, so let's talk about the inside single cycle time loop use case. So you can think about each iteration of a single cycle time loop. You can think of that as a single clock cycle. So every iteration of a single cycle time loop is going to take one FPGA clock cycle. Okay, so most of these FPGA math and analysis VIs, when you set it to execute inside a single cycle time loop, they're multi-cycle. This means that these functions take more than one cycle to return a valid result. If you place one of these multi-cycle nodes inside a single cycle time loop, well, the function is not going to return a valid value during every single clock cycle. Okay, the throughput rate of that function and the values of the handshaking terminals that you saw will determine the clock cycles during which this function actually produces a valid value. So let's talk about what throughput and latency is. So you can think about throughput as the number of cycles between accepting a new input. Okay, so it's kind of like the number of cycles, which is kind of the same thing as single cycle time loop iterations, right? And let's take a look at latency. So latency is the number of cycles before producing a valid result for the corresponding input. Okay, so we'll talk about these two a little bit more on the next slide, where we can see it graphically what that means. So let's take a look at the context help real quick. So notice on the context help for both of these functions, we've set them to the execution mode to be inside a single time loop, as you can see near the bottom. And then in red, notice that you can see in the context help what the throughput is and what the latency is. Okay, so if you take a look at the scaled window, the throughput is 1 cycle per sample. That means every single cycle of the time loop, it can accept a new input. But the latency is 3 cycles. That means the output associated with an input is only going to happen 3 cycles later. So again, let's talk about this in the next slide, and we can see it visually. Okay, so in this slide, we're going to talk about throughput and latency a little bit more. Okay, in this case, we have the high throughput square root function, and the way that we've configured it, it's going to execute inside a single cycle time loop, and we're going to have a throughput of 2 cycles per sample and a latency of 8 cycles, as you can see in the context help. Okay, so what does that mean? So let's talk about throughput first. Okay, so here we see a graph, and on the x-axis, we see the single cycle time loop iteration. So we'll have iteration 0, iteration 1, 2, 3, 4, 5, and so on. And we'll see how this function executes relative to that. Okay, so let's take a look at the inputs. So here we see A, B, C, D, and E. Those are our inputs. And A prime, B prime, C prime, D prime, and E prime are the outputs that are associated with that input. Okay, so if we're looking at the throughput, notice that this function is able to accept a new input every 2 cycles. Okay, so notice that in iteration 1, it was able to get A, and then iteration 3, it's able to read B, and then iteration 5, it's able to read C. Okay, so that's what throughput is, how often this function will be able to accept a new input. But let's take a look at the latency and how that affects things. So if we look at the latency, it's 8 cycles. So notice that we're reading in the input A at cycle number 1, and then at cycle number 9, 8 cycles later, we're outputting A prime, which is the output associated with our input A. Okay, so notice if we were running this function inside a single cycle time loop, we're gonna have to wait 8 cycles before this function even produces its first valid output. But afterwards, it's going to be producing valid outputs every 2 iterations. So after that initial latency, we're going to get a pretty nice throughput. So every 2 cycles, we'll get a new valid output. So the way that this is implemented is these functions actually have an internal pipeline that's going on. So this is why you kind of see this pipeline behavior. Okay, on this slide, I want to talk about VI throughput latency and the way that the FFT Express VI can implement it, because it's a little bit different. Okay, so let's take a look at the context help for this FFT. Okay, so notice the length of this FFT is 64. We also have a throughput of 4.07 cycles per sample, which right now it sounds a little bit weird, but we'll explain that. And the latency here is 228 cycles. Okay, so let's take a look at what's going on. So first, let's take a look at frame A. So what's going on is, if we look at frame A, the FFT Express VI, it's going to be inside a single cycle time loop, and for the first 64 inputs, it's going to get each input right in a row. So for 64 iterations in a row, it's going to get 64 inputs. Okay, and then if we look at the latency, it's actually going to wait until 228 cycles later for the output of each input to be output. So notice that over here, we've got 64 inputs happening at the beginning, and then you see the latency drawn there. The red line that you see there is equivalent to 228 cycles. Okay, so 228 cycles later, you start getting the outputs that are associated with those 64 inputs. And those 64 outputs will be output 64 iterations in a row. Okay, the other thing now is, let's talk about the throughput. So if we take a look at the throughput, notice that frame A is able to start getting those 64 inputs, and then we go down to frame B. So frame B is actually not going to be able to start getting inputs until this function is halfway done with outputting those 64 outputs with frame A. So that's kind of what you're seeing. There's a little lag there before frame B can start getting its inputs into the FFT Express VI. Okay, so if we're looking at those calculations, it's going to be 260 cycles between the start of frame A and the start of frame B. So if we do a calculation for that for the throughput, we've got 260 cycles that are going on in between the start of A and B, but during those 260 cycles, we're getting 64 inputs of valid inputs, and that's what we see in frame A. Okay, so if you do 260 total cycles divided by those 64 valid inputs that we're getting in, we essentially get a throughput of 4.07 cycles per sample. Okay, so that's how we arrived at a seemingly strange throughput of 4.07 cycles per sample. So this was just kind of a quick explanation of the FFT Express VI. I encourage you, if you're going to be using an FFT in a single cycle time loop, to go ahead and look at the help for this function. And there are other configurations that are associated with this function, so that'd be good to read up on. But I just wanted to talk about this particular use case, just because at first it seems a little strange. But hopefully now you understand it. Now let's talk about VI latency and clock rate. So the clock rate is going to specify the maximum clock rate at which this function can compile. So if we look here on the right, we notice that there is a slide bar for clock rate, and we've moved it all the way to high. So we want this function to execute at very high clock rates. Now let's go back to that second bullet. So a faster clock rate is going to require more internal pipelining stages. Okay, so that means that latency is going to increase because there's more pipelines, and also it's going to use more FPGA resources to implement that pipeline. So if we look at the screenshot on the right, we've made the clock rate very high, so the throughput is going to be smaller, which means we're going to get more throughput, but the latency is going to be 6 cycles, so it might increase the latency here. In the previous section, we described the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. By the end of this module, you will be able to use the 4-wire handshaking protocol when using multi-cycle FPGA math and analysis VIs. So in the previous module, we talked about how on the FPGA math and analysis VIs, you can either use them outside of a single cycle time loop or inside a single cycle time loop. So remember, if we were setting it to run inside of a single cycle time loop, a lot of these VIs are going to be multi-cycle, right? And we're going to get these extra terminals here. So on this slide, we see that there's the input valid, there's ready for input, there's output valid, and ready for output. Okay, so imagine this block diagram is sitting inside a single cycle time loop. Now we're just going to explain some high-level concepts about these handshaking terminals, and in the next slide, we'll talk about a specific example to try to make it a little bit more clear. So in a single cycle time loop, handshaking is necessary because multi-cycle nodes need more than one cycle to compute valid data. But the single cycle time loop forces these nodes to return data every single clock cycle. Therefore, the multi-cycle nodes do not return valid data every single clock cycle necessarily, and that's due to the throughput and latency. So to ensure the numerical accuracy of an algorithm, these nodes that depend on the data must know whether the data is invalid or valid. So here we've got a handshaking protocol that you can use with certain nodes inside a single cycle time loop. This protocol involves the terminals that you see on this slide. So the first one, input valid. This is going to specify that the next data point has arrived for processing. And the next one we see there is the ready for input. This one is going to indicate whether the node can accept a new data point during the next clock cycle. Next we see the output valid. This one's going to indicate that the current data point produced by the node is valid and ready to be used by downstream nodes. And then lastly, we see the ready for output. This one is going to specify whether the downstream node can accept a new data point. So let's quickly talk about this example here. So we see that there is a ready for input terminal right there, and what that's going to say is, okay, this node is now ready to accept inputs on the next iteration. This is why we're wiring the ready for input into a feedback node. So the next iteration, the upstream node knows that our VI is ready for an input. So the upstream node is going to be able to say whether it's sending valid data or not, and that's going to go inside the input valid. So if our middle node here is ready for an input and it sees that the input valid is true, it's going to go ahead and take that data and start processing it. Now let's talk about the output valid and ready for output. So the downstream node is going to let our middle node know whether it's ready to receive a valid output yet. Okay? So the downstream node is feeding that into a feedback node. And that feedback node is telling it on the next iteration, the middle node will know whether the downstream node is ready for an output. And if it's ready for an output, then our middle node will send output valid and send it a true value, as well as outputting the valid output data. Okay, so let's take a look at a practical example of VI handshaking. Okay, so here let's take a look at what we got on the block diagram. We've got two multi-cycle nodes inside a single cycle time loop. The first node we see is a scaled window. So the scaled window has a throughput of 1 cycle per sample and a latency of 3 cycles. That means the scaled window is going to be able to accept the new input every single cycle. But the latency, the output associated with each input, is going to happen 3 cycles later. Now let's take a look at the FFT one. So that is going to have a throughput of 4.07 cycles per sample and a latency of 228 cycles. So we won't get too much into that in this particular example, but you're going to see how these different handshaking terminals work. Okay, so on the chart, we see an example of what actually happens with these nodes. So let's look at loop iteration 0. Okay, so on loop 0, both the scaled window and the FFT VIs are going to have a ready for input of false. That's because it's basically doing some initialization in that first cycle. Okay, so let's go to loop 1. So in loop 1, scaled window and FFT are both going to be ready for input. So that's why those are set to true. Okay? So the ready for input is telling the upstream nodes on the next cycle that these nodes are ready for input. So let's go to the next cycle. So let's go to loop number 2. So in loop number 2, because the scaled window VI is ready for input, it's going to consume data A. Okay, so it's going to consume A, but the output valid of scaled window is still going to be false. The reason why is it's going to have to wait 3 cycles of latency before that output is going to be valid. Okay. Now let's look at the FFT node. So the FFT node is still ready for input, because the output valid of our first one, the scaled window, is still false, the FFT node is just kind of waiting there for its input valid terminal to be set to true. Okay. So let's go to loop number 3. So the scaled window, because its throughput is 1 cycle per sample, it's able to consume its next piece of data. So it's going to consume B, but output valid is still false due to the latency. FFT, in the meantime, is still waiting for its input valid to be set to true, but in the meantime, it's still ready for input. So it's going to output ready for input true. Let's go to loop number 4. So in loop number 4, scaled window, again, because of its throughput, it's going to be able to consume C, but the output valid is still false because of that latency. FFT, in the meantime, still waiting for a valid input. And finally, let's get to loop number 5. So in loop number 5, scaled window, it's going to consume D, and finally 3 cycles of latency have passed, so now the output valid is true. And because the output valid is true, let's go to the FFT node. The FFT node is going to see an input valid of true, so it knows it's valid input, and it's going to be able to consume A prime. Okay, so now let's talk about FPGA loop throughput and latency. So we're going to talk about the throughput and latency for the entire loop if it has multiple multi-cycle nodes in there. Okay, so if you have a series of nodes inside a single cycle time loop, the throughput for that entire series of nodes is going to be limited by the throughput rate of the slowest node. Okay, so the slowest node technically has the largest cycles per sample, right? So if we take a look at this example, you'll see that out of all these nodes, the highest throughput we see is 4.07 cycles per sample, right? So that particular node is going to have to wait about 4.0 cycles per sample, which is going to slow down the rest of the nodes. Okay, so the throughput for this series of nodes is going to be 4.07. Okay. Now let's talk about latency. So the latency for a series of nodes inside a single cycle time loop, you're just going to add up the latency of all the nodes in your series. So in this case, we're just going to add them all up, and that's going to be the total latency for that series of nodes. Last thing I want to talk about is use caution when branching wires inside here. So it's important to consider node latency when you're branching wires. If the latency between 2 parallel branched paths is different, data along those 2 branches may not be correlated. So at this point, I would recommend that you do exercise 7.2, 4-wire handshaking protocol. These handshaking terminals, since there's 4 of them and there's 4 wires, a lot of times it's referred to as 4-wire handshaking protocol. So in this exercise, you'll be able to actually wire some of these VIs together and configure them, and this will give you a better idea of how throughput, latency, and these handshaking terminals work. So for now, let's go ahead and take a look at the solution, and I'll demo that. Okay, so let's jump into the solution for exercise 7.2, 4-wire handshaking protocol. So I'm going to open this up and notice that this VI is running on our FPGA. And let's look at the block diagram real quick. So this is the same block diagram that you saw in the previous slide. And notice that we've got a series of nodes here. Okay. So notice that there's the input valid, so all these handshaking terminals, and they're wired together in the way that we described in the slides. So some of them are going to have feedback nodes, and they're going to be wired to each other. So we just explained this on one of the previous slides with a table and kind of walked through that, but I would highly recommend that you do this exercise yourself also, so you can have some experience building it in case you need to increase the throughput of some of your algorithms inside a single cycle time loop. So for now, what I want to do is I want to talk about the throughput for this series of nodes right here. Okay, so if we want to take a look at the total throughput, what is this going to be limited by? Well, remember, it's limited by the one with the slowest throughput. In this case, the slowest throughput is 4.07 cycles per sample. Okay, so we would expect that if we were trying to calculate that, the throughput for this series of nodes or this loop is going to be 4.07 cycles per sample. Okay, so the way that we're going to calculate that is we've got a counter here. So this counter is going to count how many cycles or iterations that this single cycle time loop is going through. And then we have another counter here that is going to count how many valid samples we get. So notice that if output valid here is false, we're going to go to the false case and not do anything. Okay, but once the output is valid, so every time we have a valid output, we're going to go to the true case and we're going to count that, and we're also going to display it on our indicator. Okay, so based on these two indicators, we should be able to calculate the throughput for this series of nodes right here. Okay, so let's go to our front panel. Let's go ahead and run. So now it's just going to run for a bit. I'm just going to let it run for a while so we can get some bigger numbers, and now I'm going to stop it. So let's go to our calculator here. So if we take our total number of cycles right here, which is 148095, and then we divide that by the number of valid samples we got, which is 36416, we get a throughput that is pretty close to 4.07 cycles per sample. So here we've just shown how you can calculate the throughput for a series of nodes, and go ahead and do the exercise now, and you can get some experience actually building that block diagram. In the previous section, we used the 4-wire handshaking protocol when using multi-cycle FPGA math and analysis VIs. By the end of this module, you will be able to perform high-throughput math. In this section, we're going to be talking about the high-throughput math functions. So what you see on this slide is the high-throughput math palette. This is a palette that is within the FPGA math and analysis palette. The functions that you see on this palette you can use to achieve high FPGA fixed point math and analysis rates. So you can place these in single cycle time loops and use these to achieve very high throughput. So all these operations are supported inside the single cycle time loop. Notice that there's a divide function in here. So this is going to allow you to divide inside a single cycle time loop. Also, there's a number of operations on here that are not available in your basic numeric palette. So for example, you see that there's trigonomic and also logarithmic functions on here that you can access. So in this slide, we have an example of one of the high throughput math nodes. In this case, we're looking at the divide function. So if you use this one, notice that you can double click it and you get some configuration options. So notice that you can configure the fixed point configuration, as you can see in red, and also you can configure the throughput as well. So as you're changing things up and changing the fixed point configuration, that could also affect what kind of throughput you can get. So on this slide, we see that the high throughput math functions are kind of similar to the FPGA math and analysis functions that we talked about before. So here we see that you can also configure it to execute outside a single cycle time loop or inside a single cycle time loop. So if you want to get higher throughput rates, you would want to execute this inside a single cycle time loop. And notice over here, you can also configure its throughput. So if you take a look at this particular example, notice that in red, you see a setting there for throughput. You can adjust that for different throughputs. So for example, on the slide, you see that it is set to 17 cycles per sample. And if you look at the bottom there, notice that there is a throughput of 17 cycles per sample, and the note that goes with it is that the latency is 18 cycles. So you can see that through this configuration, you can figure out what the throughput and latency is going to be depending on your settings. So notice that at the very bottom, you see a throughput of 4 cycles per sample. So let's say we had adjusted that setting and we changed it to 4 cycles per sample. Notice the note that comes along with it. At the bottom, the note says that this function has a 5-stage pipeline. So to achieve that throughput of 4 cycles per sample, there was an internal pipeline that was built into this, and that's how that throughput was achieved. On this slide here, we see another subpalette. So this is a palette that you'll find within the high throughput math palette. So this palette is called Basic Elements, and the nodes that you see here you can use to perform low-level FPGA operations. So you see that there's one for accumulating totals there. You can also delay signals with a discrete delay in case you need to line up signals and things like that. You can do some binary arithmetic, and for these low-level functions, a lot of times you might use this as a building block in a more complex algorithm. So you might not even need to use these at all. The last thing I want to talk about there is the DSP48 node. So to achieve higher performance, you can use the DSP48 node to directly control the dedicated DSP hardware on the FPGA. While this offers the higher performance, it also introduces significant design complexity and also ties the design to the specific FPGA target or chip. So that'll limit future algorithm portability. So for example, if you're using one of these DSP48E nodes and you're trying to port it over to another FPGA target that doesn't have that exact same DSP slice, then it's not going to work. So in general, we see that there's a lot of different options for you for FPGA math and analysis. There's a numeric palette, there was the high throughput palette, and there's even things like the DSP slice. So just know that all these are at your disposal, and you can choose them as necessary. Now you can perform high throughput math. Next, we will describe resources for integrating third-party intellectual property. In the previous section, we performed high throughput math. By the end of this module, you will be able to describe resources for integrating third-party intellectual property. In this section, we'll talk about ways that you can integrate third-party IP. So first, we'll talk about the Xilinx core generator IP, and then we'll talk about other third-party IP. So in this slide, we see the Xilinx core generator IP. If you want to integrate this IP into your FPGA VI, what you can do is, by using this, you can access a large collection of IP that was created by Xilinx, and it's fine-tuned for Xilinx FPGA hardware, so it's going to be very optimized. The supported IP, though, varies by FPGA target. So if you open up your FPGA VI for a particular target, and you go to the block diagram, if your target supports it, you'll see a functions palette for Xilinx core gen IP. And then from there, you can browse it and look at the different algorithms that are available. So you can see that there's video and image processing, there's digital signal processing as well, and some other things. So feel free to browse this palette and see what's already been made for you, so you don't have to do the work and try to implement those algorithms yourself. So let's say you already have some third-party IP and you want to integrate that IP into your FPGA VI. Well, you can do this by using the IP integration node. So using that, you can import IP from other IP synthesis files. So if you have the VHD or XCO or NGC files, you can use these and import them into your LabVIEW FPGA VI. So when you're using the IP integration node, you have to place it inside a single cycle time loop, and you also need to make sure that the IP that you're importing meets the requirements of the IP integration node. So for more information on this, if you're trying to do that, go to the Using the IP Integration Node topic in the LabVIEW help, and you can get a lot more details on this there. Okay, so on this slide, we just want to point you to some additional resources. So if you look at that link there on the top right, ni.com/ipnet, this is a place where there's a collection of FPGA IP and examples. So these are gathered from internal NI developers and also the LabVIEW FPGA community as well. You can go here, you can browse, you can learn, you can download LabVIEW FPGA functions or IP. You can even take your own IP and share it with the community as well. So this is just another place that you can go to, and you can browse the different categories, see what IP you can find, and if someone else has already implemented what you want and has uploaded it here to this community, then you can just download it and save some development time.